All right, let's just jump right into this explainer. Today, we're going on a chronological journey, following a single piece of metal from a totally raw billet to a flawless flight-ready part. It is an absolutely incredible transformation of heat and pressure. And honestly, it's a process that essentially powers the modern world, from the car you drive every day to the commercial planes you fly in.
You know, humans have been hitting hot metal with hammers to make swords and horseshoes for literally thousands of years. But modern forging, it is a highly precise, multi-stage science. We aren't just hammering metal into shape anymore. We're completely re-engineering its internal structure from the inside out so it can withstand extreme industrial forces.
To put that into perspective for you, a modern carbon steel billet has to be heated up to 1250 degrees Celsius. That is roughly a quarter of the temperature of the surface of the sun, and we have to do that before we even begin to shape it. At that temperature, the steel glows this brilliant, blinding orange. It's a completely extreme environment, completely necessary for an extreme process. So here is our manufacturing blueprint for today. We're going to follow 6 distinct phases: preparation, temperature, deformation, post-forging, finishing, and finally inspection. Let's get to it.
Starting right off with phase 1, preparation, heating the billet.
Every single flawless part starts its life as a raw chunk of metal, which we call a billet. This billet gets cut to the exact required size using a heavy-duty bandsaw or shear, and then it is rigorously checked for surface defects. Why are we so incredibly careful right out of the gate? Well, because a single tiny surface defect now will multiply and completely ruin the structural integrity of the part later when it's under all that extreme pressure. Moving right along to phase 2, temperature, cold, warm, and hot. It's honestly fascinating how much these temperatures vary depending on the material. I mean, the gap between carbon steel and aluminum is huge, but notice a key trend here. We always forge well below the actual melting point. Usually, it's around 70% of the absolute melting temperature. We want the metal to become soft and doughy so it can flow perfectly, but we definitely never want it to turn into a liquid puddle. Now, if you really want to understand hot forging, you've got to grasp this concept, the recrystallization temperature. Hitting this specific thermal sweet spot makes the metal incredibly malleable without breaking its spirit. Basically, it allows the metal's internal grain structure to seamlessly deform and rebuild itself at the exact same time. That prevents what we call strain hardening, which essentially keeps the metal from becoming brittle while we smash it. So you're probably wondering, why choose one over the other? Well, cold forging takes place in your room temperature. It saves a ton of energy and holds incredibly tight dimensional tolerances, but you're mostly limited to smaller, symmetrical shapes under 25 pounds. Hot forging, on the other hand, lets us make massive, complex shapes without needing unimaginable force. Plus, it beautifully refines the internal grain structure for added strength. Oh, and there's also warm forging, sitting right in the middle, giving us a really nice balance of both. Now, for the really high-end stuff like advanced aerospace superalloys and titanium, we use isothermal forging. This is a highly specialized process where both the metal and the actual forging dies are heated to the exact same temperature, usually inside a vacuum so it doesn't oxidize. This guarantees the metal doesn't cool down a single degree the second it touches the die, which gives us total control over the strain rate. Okay, phase 3, deformation, shaping the metal. Once our metal is perfectly heated, we've arrived at the main event. There are quite a few ways to apply that localized compressive force. We've got massive hammers dropping in milliseconds and slow, continuous presses. There's upset forging, which compresses a piece's length to bulge its diameter out. Think of making the head of a bolt. And roll forging, squeezing the metal through cylinders. Seriously, some automatic hot forging machines can pop out an absolutely wild 180 parts per minute. The absolute key takeaway here is the massive difference in time and force. Drop hammer forging is an instantaneous impact. We're talking milliseconds. So it mostly deforms the outer surface. Press forging, that's a slow squeeze over several seconds. It controls internal strain by working the entire core of the metal, not just the surface layer. All right, phase 4, post-forging, trimming, and treating. So the metal is shaped, but we are definitely not done. In close die forging, you get this extra metal squeezed out between the two halves of the die. It's called flash. Now, this actually helps build intense pressure inside the die cavity so every little corner gets filled. But once the part is shaped, that flash has to be mechanically trimmed away immediately with a specialized press. And then we get to the chemistry side of things. There's just a massive glossary of complex heat treatments we can use to manipulate the newly forged metal's internal structure. Because once the part cools down, its internal stresses are sky high. So we run it through specific thermal cycles to dial in the exact mechanical properties the engineers are looking for. Think of this three-step heat treatment kinda like, well, like finishing a really great meal. First, we let the metal rest and cool in still air to relieve forging stress. That's normalizing. Then we flash cool it super fast in oil or water to lock in incredible strength. That is quenching. And finally, we temper it. We reheat it just slightly so the steel isn't too brittle, completely restoring its tough, impact-resistant nature.
Which brings us to Phase 5, finishing, machining, and coating.
We're moving from the loud, earth-shaking machinery down to the micrometer level now. Forging gets us the raw shape and brute strength for sure, but we rely on secondary operations to really finish the job. We use shot blasting to blast away the rough forging scale, and CNC machining to hit those exact, perfect dimensions. Then we protect it, applying specialized coatings like hot dip galvanization for a heavy-duty rust barrier or black oxide for a sleek, corrosion-resistant finish. And finally, Phase 6, inspection, guaranteeing structural integrity. This brings up a genuinely fascinating problem. I mean, think about it. If a microscopic internal void or some hidden crack could cause a jet engine part to fail mid-flight, how do we find it when it's buried deep inside a solid block of steel? You can't exactly just break it open to check. The answer is non-destructive testing, or NDT, and it is literally incredible what we can do now. We utilize everything from penetrating dyes that find microscopic surface cracks to magnetic fields that reveal hidden subsurface flaws. We even bounce ultrasonic sound waves straight through the solid metal, or use heavy-duty industrial X-rays, ensuring the internal grain structure is utterly perfect, all without ever damaging the finished part. So, tying this all together, why does forging win out over other methods like casting? It's all about that grain flow. Because of this intense journey of extreme heat, immense pressure, and precise thermal treatments, forged parts just offer unmatched strength. By physically squeezing the metal, we align its continuous grain flow to perfectly match the shape of the part, giving it vastly superior fatigue resistance and impact toughness. The next time you fly in a plane or drive a car, will you remember the invisible, perfected grain structure of the forged metal keeping you safe? It kind of completely changes how you look at the industrial world around you, doesn't it? The next time you hit the brakes or see a jet engine spinning, just remember the intense journey that metal went through. These aren't just hunks of metal, they're highly engineered marvels of metallurgy, molded by extreme forces. Thanks for joining me on this explainer, and keep your curiosity sharp.